There is a cloud of atoms in a laboratory in Colorado, small enough to rest on the tip of your finger, and time does not pass through it evenly. The top of that cloud ages faster than the bottom, not by hours, not by minutes, but by a fraction so impossibly thin that no instrument in human history could have detected it until now. In February 2022, a team at JILA measured this difference for the first time, across a gap of just 1 millimetre. The clock that made it possible ticks 429 trillion times every second. It will not gain or lose a single second in 15 billion years. It does not measure time the way you have always understood it. It measures the bending of the universe itself. For most of human history, no one imagined a clock could do such a thing. Then across 3 remarkable decades, a handful of physicists in Tokyo, Munich, and Boulder quietly built instruments that changed what the word precision means. What they discovered reaches far beyond timekeeping, into the shape of the Earth, the hunt for dark matter, and some of the deepest unresolved questions in all of physics. In this video, we trace the path from the first trembling caesium atoms to the nuclear frontiers that may soon redefine the second itself. If this is the kind of content you value, consider subscribing and leaving a like. It genuinely helps. This is Quantum Questions. The story starts now. Time, for most of human existence, was something you watched. The shadow inching across a sundial, the swing of a pendulum, steady enough to feel trustworthy, slow enough to count. The turning of the Earth on its axis, dragging the sun across the sky in an arc that marked the passage of a day. For thousands of years that was enough. Time was bound to the physical world, to objects large enough to hold in your hands, to motions you could observe with the naked eye. Every civilization anchored its calendar to something visible: the moon, the harvest, the flooding of a river. But there was a problem with all of it. Pendulums slow down, their swings shorten with temperature, lengthen with humidity, shift with the imperceptible warping of the metal they hang from. Quartz crystals, introduced in the 20th century, were better. A thin sliver of quartz vibrates at a predictable frequency when voltage is applied, but they drift too, aging quietly inside their casings, losing their sharpness year by year. And beneath all of these, the Earth itself turns out to be an unreliable timekeeper. Its rotation is not constant. Tidal friction from the moon drags against it. Earthquakes redistribute mass. The slow churn of the mantle shifts weight from one hemisphere to another. A day today is not the same length as a day 100 million years ago, and it will not be the same 100 million years from now. The unit of time that civilization depended upon, the second, was defined by something that was quietly, constantly changing beneath our feet. The idea that nature might offer something better took shape in the 19th century. James Clerk Maxwell, the Scottish physicist whose equations unified electricity, magnetism, and light into a single framework, observed that atoms vibrate at fixed, reproducible frequencies. Frequencies set not by craftsmanship or environment, but by the fundamental structure of matter itself. Lord Kelvin echoed the thought: if you could harness those vibrations, you would have a clock that did not depend on anything mechanical, anything manufactured, anything that wore down with use. The ticking of an atom would be the same today as it was 1 billion years ago, and the same 1 billion years from now. It would be a standard that belonged not to any nation or any era, but to nature itself. It was an extraordinary insight, but the tools to act on it did not yet exist. The atom was too small, too fast, too far beyond the reach of 19th century instruments. The idea sat waiting, like a seed in dry ground, for nearly 100 years. The person who finally made it real was Isidore Rabi, a physicist at Columbia University in New York. In the 1930s, Rabi developed a technique called atomic beam magnetic resonance, a way of probing the exact frequencies at which atoms transition between quantum energy states. He fired beams of atoms through carefully shaped magnetic fields, applied radiation at specific frequencies, and watched for the precise point at which the atoms responded. The technique was elegant, reproducible, and grounded in the mathematics of quantum mechanics. It earned Rabi the Nobel Prize in Physics in 1944. The following year, in a conversation with a reporter, he made a suggestion that would quietly reshape civilization. His method, he said, could be used to build a clock. Not a clock that measured the swinging of a weight, not a clock that depended on the vibration of a crystal. A clock that measured something far more fundamental, the quantum behavior of matter itself, the natural resonance of an atom. What followed happened faster than anyone might have predicted. Within a decade, the first experimental atomic clocks were running in laboratories. Within 2 decades, the second itself, the most basic unit of time in science, commerce, navigation, and daily life, had been stripped away from the spinning of the Earth and anchored instead to the behavior of a single element. The age of atomic timekeeping had begun, and the world, though most of it did not yet realize it, would never measure anything the same way again. To understand how an atomic clock actually works, you need to sit with one of the strangest and most beautiful facts about the quantum world. Every atom of the same element is identical, not similar, not approximately the same. Identical. A caesium atom in a laboratory in London behaves in exactly the same way as a caesium atom in Tokyo, or drifting through the cold vacuum between galaxies, or sitting on a rock on the far side of Mars. This is not a useful approximation. It is not a simplification for the sake of convenience. It is a consequence of quantum mechanics, a law so precise, so absolute, that no experiment in the history of physics has ever found it to fail. Each atom has a set of discrete energy levels, not a smooth ramp, but specific defined states, like the rungs of a ladder with fixed spacing that nothing can alter. When an atom absorbs electromagnetic radiation at exactly the right frequency, the frequency that matches the energy gap between 2 of those rungs, it jumps from a lower state to a higher one. When it falls back, it releases radiation at that same frequency. The frequency is not a choice. It cannot be tuned, adjusted, or worn down by time. It is determined by the fundamental constants of physics, written into the architecture of the atom itself. An atomic clock exploits this with beautiful simplicity. It generates a signal, a beam of microwave radiation, or in newer designs, a beam of laser light, and tunes that signal to match the exact frequency of a chosen atomic transition. If the signal is at the right frequency, the atoms absorb it and jump between states. If the signal drifts even slightly off resonance, fewer atoms respond. By monitoring how many atoms make the transition, the clock continuously nudges its signal back toward the peak of the resonance. Each completed cycle of that locked signal becomes 1 tick, and those ticks are the same everywhere in the universe, for every atom of that element, for all of time. The contrast with everything that came before is stark. A mechanical clock depends on the quality of its springs, the smoothness of its gears, the constancy of its surroundings. Change the temperature, and its rate shifts. A quartz clock depends on the purity of its crystal, which degrades slowly as the years pass. An atomic clock depends on the laws of physics. And the laws of physics, so far as anyone has ever been able to determine, do not degrade at all. But there is a catch, and it is a serious one. To measure an atom's resonance frequency with extreme precision, the atom must be nearly motionless. Any movement introduces what physicists call a Doppler shift, the same effect that makes an ambulance siren sound higher pitched as it rushes toward you and lower pitched as it pulls away. For atoms, even modest velocities blur the transition frequency, smearing the sharp resonance line into something broader and harder to pin down. The faster the atoms move, the fuzzier the measurement becomes. And an atom at room temperature is not gently drifting. It is racing at hundreds of meters per second, colliding with its neighbors in a chaotic storm of thermal energy. This was the central challenge of early atomic clocks. The atoms were hot, fast, and maddeningly difficult to hold still. The solution, cooling them to within a whisper of absolute zero, slowing their frantic motion until they barely moved at all, would take decades of ingenuity, multiple Nobel Prizes, and some of the most delicate experimental work ever performed. And when it finally arrived, it would change everything. The first atomic clock arrived in 1949, built at the National Bureau of Standards, the institution that would later become NIST. It used ammonia molecules as its frequency reference, and it worked, in the sense that it proved the concept was sound. An oscillating molecule could serve as the heartbeat of a clock, but the accuracy was nothing to celebrate. The ammonia clock could not keep pace with the best quartz oscillators of the day. Its transition frequency was too low, the resonance line too broad, the sensitivity to external interference too great. Ammonia had opened the door, but something far better needed to walk through it. The breakthrough came 6 years later, 3,500 miles to the east. At the National Physical Laboratory in Teddington, just outside London, a physicist named Louis Essen and his colleague Jack Parry built the first practical atomic clock using caesium. Specifically, caesium-133, an isotope with a single outer electron and a pair of quantum energy states separated by a microwave frequency of extraordinary sharpness. 9,192,631,770 oscillations every single second. Caesium had qualities that made it uniquely suited to the task. It was heavy, the heaviest stable element with a single valence electron, which meant its atoms moved relatively slowly at room temperature, around 130 meters per second compared to well over 1,000 for lighter elements like hydrogen. Slower atoms meant smaller Doppler shifts and sharper resonance lines. Its hyperfine transitions sat in a convenient microwave band, high enough to provide fine time resolution, but low enough for the electronics of the era to handle. And its quantum structure was comparatively clean, with a well-isolated transition that made systematic errors easier to model and correct than the alternatives. Essen's clock was not immediately more accurate than every quartz oscillator in existence, but it was more stable. It did not wander in the same unpredictable way, and within a few years it became clear that caesium represented an entirely new standard of reliability. Commercial caesium beam clocks followed quickly. By the late 1950s, companies were manufacturing them for around $20,000 each. A substantial sum at the time, but a price that national metrology laboratories, military agencies, and telecommunications networks were more than willing to pay. What happened next was, in its quiet way, one of the most radical decisions in the history of science. In 1967, the 13th General Conference on Weights and Measures, the international body responsible for the standards upon which all scientific measurement rests, adopted a new definition of the second. No longer 1/86,400th of a mean solar day, a definition that tied humanity's most fundamental unit of time to the uneven spinning of a planet. Instead, exactly 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the caesium-133 atom. The second was no longer an astronomical quantity, it was a quantum mechanical one, a property of a single type of atom, reproducible anywhere in the universe, invariant across all of space and all of time. Every clock on Earth, every satellite in orbit, every timestamp on every financial transaction and scientific experiment, all of it now traced back through an unbroken chain of calibration to the behavior of caesium. Humanity had untethered time from the Earth and handed it to the atom. And the atom, it turned out, was only getting started. The early caesium beam clocks were marvels, but they carried a fundamental limitation built into their architecture. They worked by firing a horizontal stream of heated caesium atoms through a microwave cavity. The atoms passed through quickly, in just a few milliseconds, and that brief window was all the clock had to interrogate them. In frequency measurement, interaction time is everything. The shorter the window, the broader the resonance signal, and the harder it becomes to identify the exact center of the peak. Imagine trying to tune a radio while only being allowed to listen for a fraction of a second. You can tell roughly where the station is. But pinpointing the center with extraordinary accuracy requires something the beam clock could not offer: more time. To build a substantially better clock, physicists needed to hold the atoms longer. And to hold them longer, they needed to slow them down. The solution came from a technique that would have sounded like science fiction a generation earlier: laser cooling. The idea was developed through the 1970s and 80s by researchers including Stephen Chu, Claude Cohen-Tanuji, and William Phillips, all three of whom would share the 1997 Nobel Prize in Physics for this work. The principle is deceptively simple. You direct laser beams at atoms from multiple directions, each beam tuned to a frequency just slightly below the atom's natural absorption line. An atom moving toward one of these beams sees the light blue shifted, Doppler shifted, upward into exact resonance. It absorbs a photon, and in doing so receives a tiny kick of momentum in the opposite direction. A nudge backward, a fractional slowing. Repeated billions of times in rapid succession, this process drains the atoms of their thermal energy, reducing their velocity from hundreds of meters per second to just centimeters per second. The atoms end up barely moving at all, cooled to a few millionths of a degree above absolute zero. At these temperatures, an atom drifts slower than a ladybird crawling across a leaf. The caesium fountain took laser cooling and turned it into architecture. A small cloud of cooled caesium atoms is gathered at the bottom of a vertical tube. A gentle upward push of laser light launches them through a microwave cavity. They rise, slow under gravity, pause for an instant at the top of their arc, and then fall back down through the same cavity, passing through it twice, once on the way up and once on the way down. The total interaction time stretches to roughly 1 full second, hundreds of times longer than a beam clock could achieve. That vastly extended observation window sharpens the resonance signal enormously, and the clock's ability to find the true center of the frequency peak improves by a corresponding factor. The intellectual foundation beneath the fountain belonged to Norman Ramsey, a Harvard physicist whose separated oscillatory field method, now universally known as Ramsey interferometry, provided the framework for interrogating atoms with two precisely timed pulses of radiation separated by a long, free drift. The atom experiences the first pulse on the way up, drifts freely through the top of its arc, and encounters the second pulse on the way down. The separation between those two interactions is what gives the fountain its resolving power. Ramsey shared the 1989 Nobel Prize in Physics for this and related contributions. NIST F1, the first American caesium fountain standard, began operation in 1999. Built by Stephen Jeffords and Dawn Meekoff in Boulder, Colorado, it achieved an uncertainty of roughly 1 second in 20 million years, a 1,000-fold improvement over the beam clocks it replaced. Its successor, NIST F2, pushed further still. The team enclosed the entire microwave interaction region in a jacket cooled with liquid nitrogen, dropping the temperature of the chamber walls to minus 193 degrees Celsius. The reason was subtle but important. At room temperature, the walls of the chamber radiate a faint glow of infrared photons, blackbody radiation, that ever so slightly tugs on the caesium transition frequency. Cool the walls, and that tug shrinks. The correction was tiny, but at the level of precision these clocks were chasing, tiny was everything. These were extraordinary instruments, the finest timekeepers humanity had ever built. But even as NIST F2 was setting records, a quiet realization was settling across the metrology community. Caesium had been pushed to the edge of what it could offer. Not because the physics was wrong, but because the frequency was too low. 9.2 billion oscillations per second had once seemed unimaginably fast. Now, against what other atoms could provide, it looked sluggish. Because there were atoms out there, strontium, ytterbium, aluminium, whose transitions vibrated not in the microwave range, but in the optical range. Not billions of oscillations per second, but hundreds of trillions. 50,000 times faster than caesium. And in the arithmetic of precision, faster oscillations mean finer divisions of time. The future did not belong to microwaves. It belonged to light. And the instrument that would make that future possible, a device so elegant it would win a Nobel Prize, was already waiting in the wings. The principle was tantalizingly simple. If precision comes from how finely you can slice a second, then the more oscillations your reference produces in that second, the more precisely you can measure it. A strontium atom, probed at the right transition, vibrates at 429 trillion times every second. Ytterbium does even better, 518 trillion. These are optical frequencies. Frequencies of visible and ultraviolet light. They are roughly 50,000 times higher than the microwaves used by caesium. In theory, switching from microwaves to light should deliver a corresponding leap in precision, like replacing a ruler marked in centimeters with one marked in fractions of a micrometer. In practice, there was a problem so severe that it stalled the entire field for decades. No electronic device on Earth could count at optical frequencies. The fastest electronics max out at tens of billions of oscillations per second. Hundreds of trillions was simply beyond reach. You could build the most perfect optical oscillator imaginable, lock it to the sharpest atomic transition in nature, and still have no way to read what it was telling you. It was as if someone had handed you a stopwatch that ticked 1,000,000 times faster than anything your eyes could follow. For years, the only workaround was a device known as a harmonic frequency chain. The idea was brute force. You started with a known microwave frequency and multiplied it upward through a series of intermediate lasers, each one locked to the next, each stage doubling or tripling the frequency until you reached the optical range. These chains were extraordinary feats of engineering and monuments to frustration in equal measure. They filled entire rooms, sometimes entire laboratory floors. 15 or more stages of frequency conversion, each one introducing noise, each connection demanding constant adjustment and maintenance. Building one was a career-length project. Running one reliably was barely less demanding. and each chain could only reach a single target frequency. If you wanted to measure a different atom, you essentially had to start again. The breakthrough came from an entirely different direction. In the late 1970s, Theodor Hensch, then at Stanford, later at the Max Planck Institute for Quantum Optics in Garching, near Munich, began exploring something hidden inside ultra-short laser pulses. A laser that fires in extremely brief bursts, each lasting only femtoseconds, millionths of a billionth of a second, does not produce a single frequency. It produces hundreds of thousands of frequencies simultaneously, spaced with extraordinary regularity across the electromagnetic spectrum. If you could see them laid out, they would look like the teeth of a comb, evenly spaced, extending from the low end of the spectrum toward the high end, each tooth a precise frequency marker. Hensch realized that if this comb of frequencies could be made to span a full octave, a factor of 2 in frequency, then something remarkable became possible. You could take any unknown optical frequency, compare it to the nearest tooth, and read off its value. The comb became a ruler for light, not a chain of 15 fragile stages, but a single elegant device that connected microwaves to optical frequencies in one clean step. The missing piece was a way to broaden the comb's reach. A standard femtosecond laser produces a comb, but one that spans only a narrow slice of the spectrum. To cover a full octave, you needed something to stretch the light. That something arrived in 1999 from an unexpected source. Researchers at Bell Laboratories developed a microstructured optical fiber, a hair-thin strand of glass riddled with microscopic air holes that altered the way light propagated through it. When a femtosecond pulse entered this fiber, something dramatic happened. The pulse broadened into a supercontinuum, a rainbow of coherent light stretching across more than an octave of frequency. The comb teeth, already precisely spaced, now reached from the red end of the visible spectrum all the way to the violet and beyond. The ruler was complete. John Hall, working at JILA in Boulder, had spent decades refining the art of precision laser spectroscopy, the measurement of atomic frequencies with extraordinary accuracy. His contributions to stabilizing lasers and referencing their output to atomic transitions were essential to making the comb a practical tool. The convergence of Hensch's insight and Hall's precision work produced something that did what an entire building of harmonic chains had struggled to do. And it fit on a single optical breadboard. A tabletop device, no larger than a modest suitcase, replacing a factory floor of lasers and electronics. In 2005, Theodor Hensch and John Hall shared the Nobel Prize in Physics for their contributions to laser-based precision spectroscopy, including the development of the optical frequency comb. The citation was understated. The impact was not. Every optical clock built since that moment depends on this invention. Without it, the precision revolution that followed would have remained permanently out of reach. The comb did not just solve a measurement problem, it unlocked an entire field. With the comb in hand, physicists could finally count light. But counting was only half the challenge. You also needed atoms that would sit still long enough to be measured with that light. And sitting still for an atom is not a natural state. Holding an atom in place requires a trap. And every trap by its very nature disturbs the thing it holds. This is the dilemma that had shadowed precision measurement for decades. To measure an atom's frequency, you need it motionless. To keep it motionless, you need to confine it. But confinement means applying fields, electric fields, magnetic fields, or the electromagnetic field of a laser. And those fields shift the very energy levels you are trying to measure. The act of trapping changes the answer. It is a problem with no obvious solution, and for a long time the best anyone could do was minimize the disturbance and correct for what remained. For charged atoms, ions, the trapping technology was well established. Hans Dehmelt and Wolfgang Paul had developed the key techniques in the middle decades of the 20th century. Dehmelt's penning trap used a combination of static electric and magnetic fields to confine a single ion in a tiny region of space. Paul's radio frequency quadrupole trap used oscillating electric fields to achieve the same goal through a different mechanism. Both earned the 1989 Nobel Prize in Physics. By the 2000s, single-ion clocks were running at NIST and other laboratories around the world, isolating one aluminium or one mercury ion in a vacuum and probing it with extraordinary control. But single ions carry a fundamental weakness that no amount of engineering can fully overcome. Quantum mechanics dictates that each time you interrogate a single atom, the result is probabilistic. The atom is either in the excited state or it is not, a coin flip between two outcomes. To extract a precise frequency measurement, you must repeat the experiment thousands of times and average the results. This quantum projection noise means that a single ion clock, however accurate in principle, requires enormous stretches of averaging time to reach its full potential. The clock knows the right answer. It simply takes a very long time to say it clearly. The alternative was obvious in concept and daunting in practice. Use many atoms at once, thousands of them, or even tens of thousands, all measured simultaneously. The statistical noise drops as the square root of the number of atoms. 10,000 atoms reduce the noise by a factor of 100. But how do you hold 10,000 neutral atoms in place, perfectly still, without disturbing the quantum transition you are trying to measure? Hidetoshi Katori, working at the University of Tokyo, found the answer. In 2001, he proposed a new kind of trap, an optical lattice. The concept used intersecting laser beams to create a standing wave of light, a periodic grid of tiny potential wells arranged in space like the cups of an egg carton. Each well holds a small cluster of atoms suspended by the electric field of the light itself. Thousands of atoms neatly arranged, all held in place by nothing but photons. The idea was elegant, but it had an apparently fatal flaw. Every laser trap shifts the energy levels of the atoms inside it. This is unavoidable. The oscillating electric field of the laser interacts with the electron cloud of the atom and pulls its energy levels slightly out of position. The size of the shift depends on the intensity and the wavelength of the trapping light. For 50 years, the consensus in the field had been clear. The only path to precision was to minimize this perturbation. Make the trap as weak as possible, correct for whatever shift remained, and accept the compromise. Katori asked a different question. What if, instead of trying to eliminate the shift, you could engineer it so that both energy levels of the clock transition shifted by exactly the same amount? If both levels shift identically, the difference between them, which is the frequency the clock actually measures, stays exactly the same. The trap is still there. The atoms still feel it. But the clock transition does not notice. The trap becomes invisible to the measurement. Katori called this the magic wavelength. For strontium, it falls at 813.4 nanometers, a specific infrared frequency at which the trapping laser holds the atoms firmly in place while leaving their clock frequency perfectly, precisely undisturbed. It was a stroke of insight that overturned half a century of received wisdom. The community had spent decades trying to eliminate all perturbations from the trapping environment. Katori showed that a carefully chosen perturbation could be made to cancel itself out, not reduced, not corrected for after the fact. cancelled at the source by the symmetry of the physics itself. The atoms were trapped, they were motionless, they were undisturbed, and there were thousands of them. In 2003, Katori demonstrated the concept experimentally with strontium atoms. 2 years later, Masao Takamoto and colleagues published the landmark confirmation in Nature, establishing the optical lattice clock as a practical reality. The paper was quiet in tone. Its consequences were not. A new architecture for timekeeping had arrived, one that combined the statistical power of thousands of atoms with the spectroscopic purity of an undisturbed clock transition. And the records it would set over the next 2 decades would make everything that came before look like a rough first draft. What followed was one of the most quietly extraordinary scientific competitions of the 21st century. 2 fundamentally different philosophies of precision timekeeping, single-trapped ions and optical lattices, began trading records with a regularity that would have been unthinkable a generation earlier. Each leap forward by one approach spurred the other to push harder. Each new record made the previous one look cautious. The result was a decade of progress that compressed centuries of previous improvement into a handful of years. The ion clock program was led, in large part, by David Wineland at NIST in Boulder. Wineland had spent decades refining the art of manipulating single-trapped ions, coaxing individual charged atoms into quantum states with a level of control that bordered on the philosophical. That work would earn him the 2012 Nobel Prize in Physics. But his most significant contribution to the story of timekeeping came earlier, in 2005, with a technique called quantum logic spectroscopy. The idea was born from a practical constraint. Aluminium possesses an exceptionally narrow and stable clock transition, one of the sharpest in nature, ideal for precision measurement. But aluminium ions are stubborn. Their internal structure does not cooperate with the standard laser techniques used to cool and detect other atoms. You cannot easily cool an aluminium ion with a laser. You cannot easily read its quantum state with a laser. By every conventional measure, it was the perfect clock atom trapped inside an uncooperative body. Wineland's solution was to give it a partner. He placed a single aluminium ion alongside a single beryllium ion in the same trap. The beryllium served as both a refrigerator and a translator. Its well-understood laser transitions made it easy to cool, and because the 2 ions were coupled through their shared motion in the trap, cooling the beryllium cooled the aluminium as well. Then came the elegant part. Through a carefully choreographed sequence of laser pulses, the internal quantum state of the aluminium ion could be mapped onto the beryllium ion and read out through beryllium's cooperative transitions. The clock atom and the logic atom worked as a pair. One held the time, the other reported it. In 2008, Till Rosenband and colleagues at NIST used this architecture to compare the frequencies of an aluminium ion and a mercury ion. The precision reached the 17th decimal place. It was, at the time, the most accurate comparison of 2 independent frequencies ever performed. A measurement so fine that it could detect a change equivalent to gaining or losing 1 second over the entire age of the Earth. 2 years later, the aluminium quantum logic clock reached an uncertainty of 1 second in 3.7 billion years. And in the same landmark experiment, Chin-Wen Cho and colleagues used it to detect something that had never been observed at such an intimate scale: the gravitational time dilation between 2 clocks separated vertically by just 33 centimeters. The clock on the higher shelf ticked faster. The difference was exactly what Einstein's general theory of relativity predicted. For the first time, the bending of space-time had been measured not between mountains or satellites, but between a tabletop and the shelf above it. Meanwhile, the lattice clock community was accelerating just as fast. Jun Ye, working at JILA, the Joint Institute of NIST, and the University of Colorado Boulder, had built one of the world's leading strontium optical lattice clock programs. Where Wineland's approach relied on the perfect isolation of a single atom, Ye's relied on the collective power of thousands. Each experimental run interrogated tens of thousands of strontium atoms simultaneously, all held in the magic wavelength lattice, all ticking in unison. In 2014, Ye's team published a landmark result in Nature. Their strontium clock achieved an uncertainty of 6.4 times 10 to the negative 18, 1 second in roughly 5 billion years. The same instrument also set the record for stability, the measure of how quickly a clock converges on its answer. It was the first time a single clock had held both records simultaneously, precision and speed in one device. The lattice approach had a structural advantage that ion clocks could not easily match. By interrogating thousands of atoms at once, it could average away quantum projection noise far more rapidly. Where a single ion clock might need hours of measurement to reach a given level of precision, a lattice clock could arrive at the same answer in seconds. The sheer number of atoms working together overwhelmed the statistical uncertainty that a single atom could never escape. On the other side of the rivalry, ion clocks held their own decisive advantage: systematic accuracy. A single ion, isolated in a near-perfect vacuum with no neighbors to jostle against, has fewer sources of systematic error than a lattice of 10,000 atoms. In a lattice, subtle interactions between neighboring atoms, tiny variations in the intensity of the trapping light from one site to the next, and the faint thermal glow of surrounding surfaces all contribute to uncertainty. Each of these effects can be measured and corrected, but each correction carries its own residual error. A single ion, floating alone in space, simply does not have most of these problems. The tension between these two strengths, stability versus systematic accuracy, many atoms versus perfect isolation, was not a weakness of the field. It was the engine driving it forward. Each approach forced the other to confront its limitations. Each record broken by one side became the target for the other. Andrew Ludlow at NIST developed a dual ytterbium lattice clock architecture that tackled one of the subtlest problems in precision timekeeping, the Dick effect. Every clock has dead time, moments between measurements when the atoms are being prepared, cooled, loaded into the trap. During that dead time, the local oscillator, the laser doing the ticking, is free-running, unsupervised, accumulating tiny frequency errors that contaminate the next measurement. Ludlow's solution was to run two interleaved clocks in the same laboratory, timed so that one was always measuring while the other was resetting. The laser was never left unattended. The result, published in 2017, set a new record for clock stability at just 1.5 seconds of averaging time. The clock could deliver a precise answer almost instantly. Then, in 2019, the ion side of the competition produced a result that seemed to belong to a different era of physics entirely. David Liebrandt and colleagues at NIST, building on the quantum logic architecture that Wineland had pioneered, constructed an aluminium ion clock that reached a total systematic uncertainty of 9.4 times 10 to the negative 19. 1 second in 33 billion years, more than twice the current age of the universe. It was the first clock to breach the 10 to the negative 18 barrier, a threshold the metrology community had long treated as a kind of conceptual horizon, a boundary between what clocks could plausibly achieve and what seemed to belong to thought experiments. The precision was so extreme that the largest remaining source of uncertainty was not the clock itself, not the trap, not the laser, not the atoms. It was the imperfect knowledge of the gravitational field at the exact location where the clock sat. The instrument had become more precise than the map of the world it rested on. These numbers had long since left the realm of practical timekeeping. No train schedule, no satellite pass, no financial transaction will ever require a clock accurate to 33 billion years. Something else entirely was happening. These instruments had become so sensitive that they were no longer merely measuring time. They were detecting the structure of space-time itself. And the question was no longer how precise can we make a clock. The question was, what can a clock this precise actually see? That question found its first extraordinary answer at JILA, in Junier's laboratory, in 2015. Tanya Nicholson, Sarah Campbell, and their colleagues published a systematic evaluation of the strontium lattice clock, reporting a total uncertainty of 2.1 times 10 to the negative 18. 1 second in 15 billion years, roughly the current age of the universe. But the number itself was almost secondary to what it implied. At that level of precision, the clock was sensitive to the gravitational time dilation caused by a height difference of just 2 centimeters on the surface of the Earth. Raise the clock by the width of your thumb. It ticks measurably faster. Reaching that sensitivity had required solving problems that earlier generations of clockmakers would not have recognized as problems at all. Mariana Safronova, a theorist at the Joint Quantum Institute, calculated the blackbody radiation shift for strontium with unprecedented accuracy, quantifying the exact frequency pull caused by the thermal radiation of the chamber walls at every temperature, and providing the correction factors that made the experimental result possible. Without that theoretical work, the measurement would have stalled at a far coarser level. The competition continued to accelerate. In 2022, Szymon Kolkowitz at the University of Wisconsin-Madison unveiled something new, a multiplexed optical lattice clock. 6 independent strontium clocks running simultaneously within a single vacuum chamber, each one a column of atoms in its own optical lattice, all sharing the same environment but operating as separate instruments. By comparing these clocks against each other, the team eliminated noise sources that affected all 6 equally and achieved a differential measurement precision equivalent to roughly 1 second in 300 billion years. Instead of building 6 separate laboratories, they had built 6 laboratories inside one. The precision had reached a point where a strange inversion had taken place. The clocks were no longer limited by what the physicists could control inside the apparatus. They were limited by what the physicists knew about the world outside it. The gravitational environment, the local magnetic field, the residual vibration of the building. The instrument had outrun the map of reality it was embedded in. And that, it turned out, was not a problem. It was an opportunity. In 1915, Albert Einstein published the general theory of relativity, a description of gravity not as a force pulling objects together across empty space, but as the curvature of space-time itself, warped and shaped by the presence of mass and energy. Among its many predictions, one stands out for its sheer strangeness. Time does not pass at the same rate everywhere. A clock closer to a massive object ticks more slowly than an identical clock farther away. Not because the clock is broken, not because some mechanical interference is dragging on its gears, because time itself, at the most fundamental level, runs slower in stronger gravity. The difference is not an illusion. It is not a measurement artifact. It is the actual physical experience of duration changing from one place to another. For most of the 20th century, this prediction was confirmed only through indirect means or across very large distances. The most famous early test came in 1971, when Joseph Haefel, and Richard Keating placed 4 caesium beam clocks on commercial airliners and flew them around the world, eastward on one trip, westward on another. When they landed and compared the airborne clocks to identical clocks that had stayed on the ground, they found discrepancies of a few hundred nanoseconds. The direction of flight determined the sign of the difference. The results matched what general and special relativity jointly predicted, down to the limits of the experiment's precision. The setup was crude by modern standards. They bought economy tickets and strapped the clocks into adjacent passenger seats. But it was the first time human-built instruments had directly shown that travelling through space and sitting in different gravitational fields causes time to pass at genuinely different rates. That result had practical consequences that now touch almost every person on Earth. The global positioning system, which became operational in the 1980s, relies on a constellation of roughly 30 satellites, each one carrying an onboard atomic clock. Those satellites orbit approximately 20,000 kilometers above the surface, where gravity is weaker and time ticks faster. The combined relativistic effects, both the gravitational speed-up predicted by general relativity and the velocity-dependent slowdown predicted by special relativity, produce a net gain of about 38 microseconds per day on each satellite clock. 38 microseconds sounds negligible. It is not. Light travels roughly 11 kilometers in that time. Without relativistic corrections, the position calculated by your phone would drift by about 11 kilometers every 24 hours, rendering the entire system useless within a single morning. The solution is built into the hardware. Before launch, each satellite clock's frequency is deliberately offset, tuned slightly slow, so that once it reaches orbit and experiences the altered curvature of spacetime, it ticks at exactly the right rate as seen from the ground. General relativity is not an abstraction confined to blackboards and lecture halls. It is baked into the infrastructure of modern navigation. But all of these were measurements made across enormous scales, thousands of kilometers of altitude, entire orbits around the planet. What the new generation of optical clocks made possible was something altogether more intimate. In 2010, Chin-Wen Cho and colleagues at NIST used a pair of aluminium-ion quantum logic clocks to detect gravitational time dilation across a vertical separation of just 33 centimeters, roughly the height of a laptop screen. The clock on the higher shelf ticked faster. The difference was tiny, a few parts in 10 to the 17, but it was real, it was repeatable, and it matched general relativity's prediction with striking precision. For the first time, the warping of space-time had been observed not between a mountaintop and a valley, but between a laboratory bench and the shelf above it. Then came the measurement that opened the chapter of physics we are living in now. In February 2022, Jun Ye's team at JILA published a result in Nature that moved the boundary of what clocks could perceive into territory that would have seemed absurd a decade earlier. Using a strontium optical lattice clock containing roughly 100,000 atoms arranged in a thin vertical column, they compared the tick rate of atoms at the top of the cloud with the tick rate of atoms at the bottom. The cloud was approximately 1 millimetre tall, 1 millimetre, smaller than a grain of rice, thinner than the edge of a key. They found a measurable difference. The atoms at the top of the cloud, farther from the centre of the Earth by a distance you would struggle to see with the naked eye, aged faster than the atoms at the bottom. The measurement achieved a differential precision of 7.6 times 10 to the negative 21. They had resolved the gravitational redshift within a single atomic sample, across a distance smaller than the thickness of a fingernail. One cloud of atoms sitting on a table in Colorado, experiencing time differently at its top and its bottom. The weight of that result extends far beyond metrology. It means that space-time curvature is not merely a cosmic phenomenon, something that matters only near black holes or across the distances between planets. It is here. It is everywhere. It is happening across the width of your hand, and we have finally built instruments sensitive enough to see it. That sensitivity has opened a set of doors that reach far beyond the measurement of time. Once a clock can detect minute differences in the local gravitational field, it stops being just a clock. It becomes a new kind of sensor, one that can probe the Earth, the universe, and the fundamental laws of nature in ways that no other instrument can match. The most immediate application is relativistic geodesy, the use of clock comparisons to map the gravitational shape of the Earth. Because a clock's tick rate depends directly on the gravitational potential at its location, comparing two clocks at different positions reveals the difference in the geoid, the surface of equal gravitational potential that serves as the reference for sea level and elevation. Traditional geodesy relies on satellite measurements and sensitive gravimeters. Optical clocks offer a fundamentally different and complementary approach, one with centimetre-level sensitivity to height differences, and one that is immune to many of the systematic effects that limit satellite methods. Hidetoshi Katori demonstrated one of the most striking early examples of this new capability. In 2020, his team transported two optical lattice clocks to the Tokyo Skytree, a broadcasting and observation tower standing 450 meters tall in the center of the city. One clock was placed at the base. The other was carried to a platform near the top. By comparing their tick rates over an extended period, the team tested general relativity at a precision of roughly 1 part in 100,000, confirming Einstein's predictions with remarkable accuracy. More importantly, the experiment proved that optical lattice clocks could function reliably outside the pristine, controlled environment of a research laboratory, that they could be transported, set up in a working building, and still deliver meaningful science. But geodesy is only the beginning. Some theoretical models of dark matter predict the existence of ultralight scalar particles, particles far lighter than anything in the standard model, that would interact very weakly with ordinary matter. If these particles exist, they would cause tiny correlated oscillations in the values of fundamental constants, including the fine structure constant and the electron-to-proton mass ratio. Different atoms respond to changes in these constants in different ways. A strontium clock and a ytterbium clock, for instance, have different sensitivities to shifts in the fine structure constant. If that constant were oscillating, driven by the passage of dark matter through the laboratory, the two clocks would disagree in a characteristic, predictable pattern. Compare them with sufficient precision, and the signature of dark matter might appear not in a particle detector buried underground, but in the frequency difference between two clocks sitting side by side on a laboratory bench. There are proposals to use networks of optical clocks separated by hundreds or thousands of kilometers as a new kind of gravitational wave detector, complementing laser interferometers like LIGO by probing a different frequency range. And there is growing interest in the idea of placing an optical clock in space. On the surface of the Earth, clocks are embedded in a noisy, variable gravitational environment. Tidal forces shift the geoid, atmospheric pressure redistributes mass. Groundwater levels rise and fall with the seasons. An orbiting clock, freed from all of this, could serve as a master reference for a global network of ground-based instruments, enabling comparisons at a level of precision that terrestrial measurements alone cannot achieve. The FOCUS mission concept, a high-performance optical clock placed in a highly eccentric orbit, swinging between low and high altitudes, has been proposed as a step toward this goal, offering a direct test of general relativity at precision's orders of magnitude beyond anything currently possible. Atomic clocks began as instruments for measuring time. They have become instruments for measuring reality itself. And the most remarkable thing about that transformation is that it may only be the beginning, because there is one more leap still to come, and it leads not outward into space, but inward into the smallest structure in all of physics. Everything described so far, every record broken, every boundary redrawn, every measurement that seemed to belong more to thought experiment than to laboratory science, has relied on a single principle: probing the energy transitions of electrons as they orbit the nucleus of an atom. The electrons are the outermost part of the atomic structure. They sit relatively far from the center, exposed to external electric and magnetic fields, sensitive to the faint thermal glow of chamber walls, affected by interactions with neighboring atoms in a lattice. All the extraordinary precision achieved by optical clocks has been won in spite of the electron's vulnerability to its environment. Physicists have spent decades learning to shield, correct, and compensate for these disturbances, and the results have been remarkable. But the electron will always be, in some fundamental sense, exposed. There is another place to look: deeper, smaller, far more protected. The nucleus of an atom is roughly 100,000 times smaller than the electron cloud surrounding it. It sits at the very core, shielded from the outside world by the electrons themselves, which act as a kind of buffer against external fields. A clock transition based on a change within the nucleus, rather than a rearrangement of the electrons, would, in principle, be vastly less sensitive to all the environmental disturbances that limit existing clocks: stray electric fields, magnetic interference, blackbody radiation, collisions with neighboring atoms. A nuclear clock would tick to a rhythm set by the deepest, most protected structure in all of matter. The problem is energy. Most nuclear transitions involve enormous jumps, energies in the X-ray or gamma-ray range, frequencies so high that no laser on Earth can produce them. A nuclear clock, for almost all known isotopes, is a beautiful idea with no practical path to realization. The gap between the concept and the technology is simply too vast. There is exactly one known exception in all of nuclear physics: one isotope, out of the thousands catalogued, that possesses a nuclear-excited state at an energy low enough to reach with light: thorium-229. This isotope has a nuclear isomer, a metastable excited state of the nucleus itself, sitting at an energy of just 8.4 electron volts. That corresponds to a wavelength in the vacuum ultraviolet, right at the edge of what laser technology can access. By the standards of nuclear physics, the energy is absurdly low. Most nuclear-excited states sit at thousands or millions of electron volts. Thorium-229's isomer is lower by a factor of roughly 10,000 than the next lowest known nuclear transition. It is a freak of nature, an accident of the complex interplay of forces inside the thorium nucleus that happens to place one energy level almost on top of another, separated by a gap just narrow enough for a laser to bridge. The existence of this state was first suspected in 1976. Leonard Kroger and Charles Reich, working at Idaho National Laboratory, noticed anomalies in the gamma-ray spectrum of uranium-233 decay products that hinted at a very low-energy nuclear level in thorium. But the evidence was indirect, and the exact energy was wildly uncertain. Early estimates ranged from 1 to 100 electron volts, a span so broad that it was almost useless for experimental planning. What followed was one of the most protracted detective stories in modern physics. For 3 decades, research groups around the world chipped away at the uncertainty, using increasingly sophisticated techniques to narrow the energy window. Each new measurement brought the value into sharper focus, but the progress was agonizingly slow. In 2003, two physicists at the PTB in Braunschweig, Germany, Eckhard Pike and Christian Tamm, published a paper that changed the trajectory of the field. They laid out a detailed theoretical proposal for what a nuclear optical clock based on the thorium isomer might look like, how it might be built, and what it might achieve. The paper was a blueprint for a device that did not yet exist, written in the hope that the experimentalists would eventually catch up with the theory. It gave the community a destination. Victor Flambaum, a theorist at the University of New South Wales in Sydney, provided the motivation. His calculations showed that the thorium nuclear transition would be roughly 5,900 times more sensitive to variations in the fine structure constant than any electronic transition used in existing clocks. If the fine structure constant, one of the numbers that determines the strength of the electromagnetic force and the structure of every atom in the universe, were drifting by even the most minuscule amount over time, a thorium nuclear clock would be the first instrument capable of detecting it. A nuclear clock would not merely be the most stable oscillator ever built. It would be the most powerful probe of fundamental physics ever constructed. For 2 decades after Peake and Tamm's proposal, the field inched forward. The energy of the isomer was gradually constrained by a string of increasingly precise experiments. Each one narrowed the window. None of them opened it wide enough to step through. The community knew roughly where the transition was. They could not yet reach it. Then in 2024, 2 things happened almost simultaneously, and the field transformed overnight. Johannes Tidau and colleagues, working across the PTB and the Technical University of Vienna, achieved the first direct laser excitation of the thorium-229 nuclear isomer. They embedded thorium atoms in a crystal of calcium fluoride, a transparent host material, and used a tunable vacuum ultraviolet laser to drive the nuclear transition. The nucleus responded. For the first time in history, a laser had reached inside an atomic nucleus and changed its quantum state. The barrier between atomic physics and nuclear physics, which had stood for a century, had been crossed. Almost simultaneously, Junier's team at JILA used a vacuum ultraviolet frequency comb, an extension of the same technology that had revolutionized optical clocks 2 decades earlier, to make the first direct frequency comparison between the thorium nuclear transition and a strontium optical clock. The 2 results together established the foundation of nuclear optical frequency metrology, the ability to measure, compare, and eventually stabilize nuclear transitions using the same toolkit that had already transformed electronic atomic clocks. Thorsten Schum at the Technical University of Vienna has pursued a complementary approach, embedding thorium ions not in a trap, but in a solid-state crystal where millions of nuclei can be interrogated at once. This opens the tantalizing prospect of a nuclear clock that could eventually be made compact. Not a room-sized research apparatus, but something approaching a portable device. The challenges that remain are real, and they are formidable. Thorium-229 is one of the rarest materials on Earth. It is a decay product of uranium-233, itself a synthetic isotope that was produced in significant quantities only during the Cold War and is no longer manufactured. The world's total supply of thorium-229 is estimated at roughly 40 grams. The vacuum ultraviolet lasers required to probe the transition are still difficult to build and temperamental to operate, and the precision achieved so far, while historic, is still many orders of magnitude below what electronic optical clocks have spent 2 decades perfecting. The nuclear clock is not going to replace the strontium or ytterbium lattice clock tomorrow. It is a beginning, not an arrival. But the principle has been proven. The nucleus can be controlled by light. And the road that Peake and Tam sketched on paper 2 decades ago is finally open to traffic. Which brings the story to the question that now hangs over all of precision timekeeping. The second, the foundation of every measurement of time on Earth, is still defined by caesium. The 9.2 billion oscillations of a microwave transition that Louis Essen and Jack Parry first harnessed in a laboratory in Teddington in 1955. It is a definition that has served civilization extraordinarily well for nearly 60 years. But the best optical clocks now surpass caesium's accuracy by a factor of more than 100. The standard has been lapped decisively and repeatedly by the instruments it was meant to calibrate. In 2022, the 27th General Conference on Weights and Measures voted to begin the formal process of redefining the second. The resolution acknowledged that optical frequency standards had reached a level of maturity that justified replacing the microwave caesium definition with one based on an optical transition. The target date is 2030, with a fallback of 2034 if the necessary conditions are not met. Those conditions are stringent. At least 3 independent laboratories must demonstrate validated optical clocks with accuracy exceeding caesium by a factor of 100. The clocks must agree with each other at that level. They must contribute regularly to International Atomic Time, the global timescale maintained by the BIPM in Sèvres, near Paris. And the metrology community must reach consensus on which atom, or which combination of atoms, will anchor the new definition. The candidates are the atoms that have driven this story from the beginning. Strontium, with its mature lattice clock infrastructure and the widest base of operating laboratories worldwide. Ytterbium, with its slightly higher frequency and record-setting stability. Aluminium, with the lowest demonstrated systematic uncertainty of any clock ever built. There are proposals for a composite definition, one that draws on measurements from multiple species. And there are voices urging patience, arguing that the decision should wait until nuclear clocks have had time to mature and show what they can truly achieve. The competition to define the second is global. NIST and JILA in the United States, the PTB in Germany, the NPL in the United Kingdom, LNE CERT at the Paris Observatory, Katori's laboratory at the University of Tokyo, the NIM in Beijing. Each institution is working toward the same goal, and the scientific stakes are matched by strategic ones. The nation or consortium that defines the second shapes the infrastructure of global time for a generation. In 2025, the Shimadzu Corporation in Kyoto began selling the world's first commercial optical lattice clock. It weighs 200 kilograms. It occupies 250 liters. It achieves an uncertainty of roughly 1 second in 10 billion years. It costs approximately $3.3 million US. It is not portable in any meaningful sense, and it is not cheap. But it exists as a product outside a research laboratory, sitting in a catalogue with a price tag. The technology that began as a thought experiment in the mind of James Clerk Maxwell has become something you can buy. The story of the clock is, in the end, a story about listening. For millennia, we watched the sky and counted its movements. We trusted the sun, the moon, the slow roll of the seasons. Then we learned to listen to something quieter, the vibrations of atoms, and found that they kept time with a fidelity the sky could never match. We built instruments around that listening, refined them, pushed them, and somewhere along the way, the clock stopped merely telling us the time and started telling us something about the nature of the universe itself. They told us that space-time bends at the scale of a fingertip, that the constants of nature might not be constant at all, that dark matter, if it exists, might whisper its presence through the tick rate of a clock. The conversation between humanity and the universe is nowhere close to finished. We have simply learned, after all these centuries, to listen more carefully. And the more carefully we listen, the more we discover that even the simplest question we ever thought to ask, "What time is it?" leads somewhere extraordinary.